Sorry for latency. So, today we're going to talk about multi-sensor scenarios. So far, we have discussed about several subjects from digital signal processing. So we started with the theory of DSP and about how to sample from an analog data and to make it as digital, to save it, to be able to save it in the computer. Then we talked about how we can represent the data in other transforms other than time domain. So we have the Fourier domain and Z domain. And for Fourier we have continuous time or discrete time. And we realized that in order to be able to process everything in the computer, we'd better to talk about the DFT or FFT, as the algorithm which implements DFT very fast. That gives us just a few number of the samples from the Fourier transform of the signal, that keeping those samples, hopefully, based on the conditions that we already talked about, if the conditions are already met, then saving those samples means saving the signal. Then we went through some processes that we can start with the digital signal, and we talked about the filtering. So we talked about two types of general filters: infinite impulse response filters, IIR, and finite impulse response, or FIR filters. Based on the different types of the filters, we can get different outputs. But in general, these filters can be applied for low-pass filtering, band-pass filtering, band-stop filtering, or high-pass filtering, depending on what, the spectrum of the signal and what portion of this spectrum belongs to the noise and what portion belongs to the signal. We can decide about which of these types of filters to use. Then we talked about how we can reduce the dimensionality of the data. In many cases, when we get the time series or the data in the time domain, we have a lot of redundancies. And it's not necessary to have all these data. And for many applications, that the data is the core or the essence of the application. And we're supposed actually to send this data, to transfer this data through any kind of medium. We'd better to have a more compressed data. Why? One of the reasons is the Shannon theory, because the channel or the medium that we send the data through is limited. The bandwidth of every channel is limited. So it's better to compress the data to have more data at a time, or to have more parallel data in one channel, in every channel. And we gave an example of mobile handsets or mobile system, the telephony. Because the channel, the wireless channel that handles the talks is band limited. So we say, for example, the GSM band. That's a band limited wireless channel. And within this channel, we need to have more subscribers that we can handle. So it means that we are allowing in every cell more talks to happen at the same time. Even though in telecommunications you might know different techniques that can increase the channel capacity or gives us the possibility to handle more subscribers, like the multiplexing in time, multiplexing in frequency. But in general, we need to have a more compressed data. But this compression should happen in such a way that we're not losing the information of the data. So if we compress the data, we transfer the data through the medium, and we get the data in the receiver, and we decode the data again, the entire process should be lossless. So we shouldn't lose any kind of information from the data, or the quality of the data should be preserved. That's the final goal. That's why we went through some dimensionality reduction techniques that can reduce the data dimensionality in one hand, but on the other hand, they try to preserve the quality of the data and the most information contained in the data. We talked about the PCA, which is a kind of projection into lower hyperplane or linear manifold from the original dimensionality of the data. Or we talked about LDA. It's also a projection, but the core concentration of LDA is on the mean of the data, while in PCA it was on the variance of the projection to be maximized. So you see, I'm reviewing the entire course, and whatever I'm saying, it might happen in your exam because it's a concept. So I'm just telling you, and these are small questions that might arise in the exam. Why PCA, why LDA, what's the difference? And one statement is your answer. And I'm giving you all the answers in just statements that I'm telling you right now. So, by far, we saw the dimensionality reduction to allow the channel containing more data, more parallel data to happen. So we talked about the PCA and LDA, but beforehand we talked about a very useful tool which was singular value decomposition, SVD. And SVD was very important because we were using SVD, or we are continuously using SVD in many signal processing and machine learning applications. SVD is important in turn because SVD always is applicable. So, contrary to eigenvalue decomposition, singular value decomposition is always applicable. Doesn't matter whether the matrix of the data which you try to orthogonalize and to factorize it is rank deficient or not. In EVD or eigenvalue decomposition, it's important. If it's rank deficient, if the matrix is singular, you're not able to find eigenvalues and eigenvectors corresponding to them in order to do this transform. But SVD transform always is applicable. Doesn't matter what kind of data matrix you have. This is another answer. So then we went through multi-resolution. So we got out of the data and the digital signal processing in general meaning, in general concept, and we went through how we can see the data with more resolution. Previously, what we had was just the data in the time, or when we do the transform or Fourier transform, Z transform, whatever, we go to another domain, which is, for example, the frequency domain or Fourier domain. But when the data stream we have, the data stream is a time series, So data varying over time. It's coming to you. You're not able to catch the entire data recorded and then to say what are the frequency components of the data. You want to do the process and to see the frequency components for every frame of data. And that frame, short frames of data, might be very short to keep the data as a stationary, or might be a bit longer to have a data in that frame which is even non-stationary. But the point is that when you cut the data into chops, small chops, you are reducing the time resolution, the frequency resolution of the data to the cost of time resolution of the data. To see more localized data in time, and sacrificing the frequency components. But the components which you are sacrificing are probably and hopefully not that much important. We went through joint time and frequency transforms. So we talked about short time frequency transform, which is frequency representation of short frames. Frequency representation of short frames. Then we talked about the kernels, which can be different in how you are taking that frame, that short frame. It can be a rectangular window, it can be a smooth window, it can be any types of window. But if that window is Gaussian kernel, then it's called Gabor transform. Why Gabor transform is important? Because Gaussian kernel or Gaussian window is the best localized window in joint time and frequency resolution. So in the Heisenberg uncertainty inequality, the equality condition comes through with the Gaussian kernel, which is the Gabor kernel. That's why Gabor transform is important. But we saw that there is a big problem inside joint time frequency representation, and that was the constant tiling strategy. It means doesn't matter for the STFT or Gabor whether you're observing the signal in the lower frequencies or in the higher frequencies. It's the same. Your behavior with the lower frequency and the higher frequencies is the same. But in many cases, the importance of lower frequencies and higher frequencies are not the same. That's why we went through new transforms, filter banks and wavelets. They are dual to each other. The only difference is that the essence, the inherent entity of filter bank, which we talk about, is frequency, but for the wavelet is scaling. So that's the difference. The only difference is that in wavelet, we are not talking about the frequencies in general, but we're talking about the scales and the resolutions. For higher part, the more resolution or less resolution. So the approximation of the signal, which is corresponding to the lower frequencies, and the details of the signal, which correspond to the higher resolutions. This is for wavelets, but for filter banks, the essence or the core of our discussion is about the frequency, which is chopped into different channels or different bands, and then for every band, we try to design a filter, which tries to just capture that part of the part of the data which can be contained in that band. But they are in general dual. So the difference between the filter bank, wavelet, and joint time frequency resolutions like the STFT and Gabor is that for filter banks and wavelets, we can have dynamic tiling of the time frequency plane. Dynamic tiling of time frequency plane. Whereas for the STFT or Gabor, we have just a constant tiling time frequency plane. So we try to see the data in the transform domain much better by the previous lecture that we had. Lecture about the multi-resolution analysis, wavelets, and field lengths. Today we're coming to a new concept, which is multi-sensor or microphone array when you're talking about a speech signal. When we're talking about a speech signal, it's called multi-microphone array. But for the images, it can be multiple microphones, multiple cameras, which are recording the same scene. So the scene or the background is the same, but it is captured or recorded through multiple sensors. We want to understand in this lecture, concentrating on the speech case, is that any difference if we just capture the data with one sensor or with multiple sensors? Does it give us a kind of advantage to have multiple recordings of the same thing or not? Or is it the same? So we see that multiple recordings is very, very useful. And it will give you more information about the data, even though they are capturing the same scene from different locations or geometries. So, and we will come to two notions of localization or localization and beamforming. And beamforming has another name in the literature you might face with spatial filtering. Spatial filtering. So filtering in the space, in the three-dimensional domain. Spatial filtering, or it's called beamforming. So a beam is formed toward a kind of, a localized part of the space. It's a very useful and very prevalent application nowadays. Many people in signal processing, including me, is working in this area. So how to deal with microphone arrays, localization, beamforming, tracking, and there are some other issues can be added to this. When you have the possibility of multiple sensors, then you also can talk about source separation. While in the single sensor is very difficult, we can talk about the source separation. MIMO communication, you have heard about that. Multiple input, multiple outputs. That's talking about multiple sensors, multiple data at the same time. So MIMO communications. These are all, starting from this slide, maybe. So, it's very simple, but very useful lecture. So, today, after all this prelude, I talked about what we said from the starting of the course so far, different resolutions, different views of the signal and transforms. Today, we're talking about multiple data. So you have multiple data, how to handle multiple data from the same signal. Please do not confuse. We are not talking about different signals. We're talking about different sample, different views of the signal. So we have different observations or different sensors. They are all capturing the same signal. So the signal is one, but it's captured from different sensors. Some people might confuse it with different signals like S1, S2, S3. I'm not talking about that at the moment. It's the subject of the source separation might be. But we're talking about one signal which is captured through different sensors. And in the sequel, in the DSP course, we will come to many other types of applications that might happen. Here we have multiple sensors. We talked about multiple resolutions. Then we will talk about multiple sources. If we have multiple sources, then what to do actually. If we have one sensor but multiple sources, then we have multiple sources and multiple sensors. These are all the combinations of the applications that you might face with in the future. So I have to talk about where to start with if you face with different types of the scenarios. So I'm trying to cover different types of scenarios that might happen in the field of signal processing. So we'll talk about the microphone array. We'll talk about how to localize a speaker. There are speakers, for example, or one speaker in the room. It might be stationary, just staying somewhere. I want to localize to get the data only from that direction and to ignore the entire data from any other directions. That's called localization. So we consider the source to be a point source. Point source means a source which is stationary in a point. For example, in three-dimensional space x, y, and z, if you say that x naught, y naught, and z naught is the point source S1, so we want to get that point source and to localize it. When we did the localization, using the spatial filtering, we want to localize the beam of the microphone array just toward this guy and to take the signal which is coming just from that point source and to ignore the signal from any other directions. That's the story of the spatial filtering. So I hope the introduction was successful, enough, and I could convey the message that I wanted. So there are different applications of microphone arrays. For example, in Sunvisor, this is a project which is handled by one of my colleagues and a group in CMU University. They try to have this equipment on 10 different cars. They used a linear microphone array on the Sunvisor. That's a linear microphone array with 8 microphones, small microphones in the Sunvisor. And they also used 4 different cameras. And there's a guy here sitting in front, and he's trying to talk, to speak with different conditions, with noise, without noise, with the window just next to him to be open. The car is stationary or car is moving with 35 miles per hour in a quiet street or in a very noisy highway. And with different conditions, the voice is captured. And accumulating the information from the voice, which is recorded, and from the camera, the system is trying to figure out what exactly he is saying. What is the use of this kind of project? One of the things which is nowadays very, very prevalent in many speech-related companies, even in Germany, is called in-car communication service. In-car communication service. What is that? It's a kind of application that people are sitting inside a car, but normally in the car, in the normal cars, it's not possible for the people to take a seat like a meeting room. So there is someone sitting in front and several people sitting behind, or maybe the car has 3 layers of the seats. So someone is talking, but the rest of the people around, it is possible for them because of the noise, because of the window, because of the cars in the highway, because of the music which is actually running, doesn't understand what exactly is said. So it's a kind of huge effort for the people who are talking to speak louder, or to lose more energy while they're speaking, or to repeat their statements quite a while. And it's bothering. In many cases it's bothering. Especially in the case that it's a kind of discussion going around. Discussion by itself might take 1 hour or 2 hours, and then you might be able, not to repeat everything, every single statement because it's just coming on time, and afterwards you might forget about that. But then one guy says that, would you please repeat your last statement? And he doesn't remember it. And many other things might happen. So it's better to have a better communication means inside the car. So the in-car communication is a kind of device tries to localize the speaker who is talking to get the more gain toward that point source, and then the reducing the entire all the other sources coming from all the other directions, and based on the speakers that might be adopted for every set, then you could just broadcast this, the output for that specific listener. So it's very useful. In general, there are many other applications. One of them is navigation system. You can talk to the navigation system, but the driver navigation system is normally in a corner of a car. It's not just in front. But the driver is actually looking just forward. He needs to look forward. And he's talking forward. So the navigation system might not understand what exactly he said. He's looking for a kind of location in a city. So he just talks about, I want to go to this place. So the navigation system should localize the driver to get the data from the driver, process it, and to see, okay, this place means this address. But if it makes mistakes, then it cannot understand it. And for the driver, it's really hard to frequently come to the navigation system. So it's interesting to know that the entire source separation stuff and the microphone, the array of sensors, it actually raised up from the seismology applications. So they wanted to know different layers of the Earth. The Earth underneath our food. What they did, they tried to make an impulse, an explosion, something like that, from the surface of the Earth, and then to capture the reflections from different sensors. Based on the reflections, they tried to do the cross correlation and whatever, just to figure out how many reflections with different types of reflections might be, and based on that, how many layers might be underneath our foot. So that started from the seismology, and it was, we can say that blind source separation actually stimulated by the seismology projects. For humanoid robot, the robotics nowadays is going through humanoid robots, which they can understand different people in the environment. They can localize toward different people, and when they localize, they can understand what exactly it says as a command or comment of something, and they can start the communication, and many other applications. There are types of the arrays or the sensor collections. So we have an application of hearing aid systems. So 50 years ago, the hearing aid was just containing a single microphone. And that single microphone was trying to capture the data from the environment and to have a gain. And then by increasing the gain, send it to the inner auditory system of the human. But nowadays, it's more sophisticated. So they try to use an array of microphones, and this array of microphones even try to localize the sources. So if you want to understand, for example, it's getting more close to the natural essence of the ears. So you can localize even to one specific source and to get the data from that location. There are arrays for radar systems. We have the phase arrays. We have three-dimensional arrays which can capture the data in a three-dimensional space. The more microphone you use and the better geometry to choose, that's very important how to get a gain in multi-sensor data. In-car communications nowadays comes with this the sun visor and the mirror visor actually. In the mirror in front, so in front of the driver, they try to provide different linear arrays, and it's mostly planar, so it's two-dimensional, but it can localize to different sources inside, for example, the driver or the one next to the driver, and also for the robotics. We have different types. So, for example, here we have probably two microphones in this left and right hand side, just the same as the human. It's interesting in the nature that human is able to localize the sound and to denoise it. It's very interesting because human are, in general doing that with just 2 ears. So the philosophy behind why we have 2 ears is that we can localize the sound. Even for the 2 eyes, so if you have just 1 eye, you will not be able to find the distance. You can see the objects, but you're not able to find the exact distance of the object from yourself. When you have 2, then in your brain a kind of process goes on and you can find the distance. For 2 ears, it's the same. So you can localize the sources and ignore many other sources coming from different locations, from different directions actually. That's why in a cocktail party problem, which actually provoked the scientists that how it's possible that you are in a cocktail party scenario, which it means that there's a babble noise around. There are many people in a cafe or restaurant or in a place, normally enclosure. Many people, groups of people around, and they're talking about different things, and you have just 2 ears. But if you want to understand what this group is saying, you can just within some seconds, you can adapt your system, the hearing system, just to localize toward this group of people and to listen to what they're saying. And after some seconds adaptation, the neural system is changed in such a way that you can just get the information from that side and ignore the other sides. But for the systems, the digital systems, it's almost impossible to get to this kind of resolution. That's why even with this much sophisticated techniques that we have in microphone arrays and source separation, still we have a huge gap between the human system, neural system, and what we have as the edge of technology and the science. So what actually, based on the knowledge, what actually human does about understanding the environment around is using 2 clues. One is called interaural time difference, and the other one interaural intensity difference. So based on the structure of the head or the scalp that the people have, with this nose in front and this structure, that's very interesting that it has been created in this way, because using this structure and this scalp gives us this opportunity to get the information. For example, there's a source here, and the acoustic source, the acoustic source is the wave which is propagated using these molecules of the air. The pressure that is actually stimulated by our energy that we put in our vocal tracts is coming out of the mouth and stimulating the air molecules and creates a wave. And this wave is propagated using the propagation formulation, whatever, and then it actually goes around the environment. So this source is stimulating the environment, but the wave propagates in the environment and then recorded by these 2 ears. One of them might have less distance than the other. And it's interesting that this system is understood by the brain. And then you can understand that this source, point source, is more is more having the trend toward the right-hand side or the left-hand side. So you try to rotate your skull toward the source based on the time difference that you have for the right and left-hand side. So you do a kind of inherent cross-correlation of the data into your brain. So you correlate the data from right-hand side here and the left-hand side inside the brain, and doing this autocorrelation, you figure out that there's a kind of mismatch in the phase, and you try to correct this mismatch in the phase, and you understand inherently, and I don't know how, you understand that, okay, the one that you got from the right-hand side is a bit earlier than the one on the left-hand side, so the source might be in the right-hand side of my three-dimensional space. That's a subject of ITD, or interaural time difference. And the interaural intensity difference is also very important. For the lower frequencies, it's interesting. For the lower frequencies, like this picture here, the propagation of the acoustic wave is almost intact for all the directions. But higher frequencies are more localized. So if this is the skull of a person, and there is a source with the low frequency here, it's almost intact, going and just penetrating in the environment. But if it's high frequency, like 6,000 hertz or 6 kilohertz, then it's more localized. It means that the intensity that the signal comes to this ear, the right hand side ear, is very high, but suddenly it makes a shadow here for the left hand side, and the intensity in this shadow drops down drastically. So for the high frequencies, the right hand side ear can understand something with a very high intensity, but the left hand side, the difference in the intensity is drastically different. So it means that if you are looking this side and someone's talking from that side, just by the intensity, you directly look back to the person, if the frequency is higher. So it means that if you want to call some person and he would not be able to listen to you, is distracted by some object, it's better to create a high frequency voice if you want him to understand. So if women calling the man, they can understand it, and they just rotate toward the location. But the other way might not work. So we have in industry, we have different types of microphones created for different types of applications. So in general, in the theory, we are dealing with the omnidirectional microphone, which means that the gain of the microphone for all the directions is the same. So it's uniform gain for all the directions. But there are very different types of microphones that you might face with. We have unidirectional, we have bidirectional, semicardioid, and shotgun, and so on. So they have gains over one direction and attenuation for the rest of the directions, or some less gain, for example, toward these four directions. And these are all based on the application. This is the gain pattern. That's called the beam pattern or gain pattern, almost conveying the same meaning of the microphones, and it's very important. So here is an example of industrial Andrea super beam array microphone, which just includes two microphones in a linear array. For two microphones, it's not much different. So we have different types of arrays. For example, even in the industry, one of the ways that the mechanics go through the faults inside the car engine is by knowing a kind of voice or a noise created by one part of the engine which is not normal. But how to localize that voice is important. So they use this kind of device, put it in front of the engine, and that tries to capture the noises from different directions inside the car engine, and then says that, for example, the noise which is not normal is coming from that part of the engine. So we just go directly to that part to fix the problem. The story of microphone array, we start with the simplest case, which is just two microphones, M1 and M2, and we put the origin in the middle of these two, the line which connects these two microphones. So if we have a point source here, somewhere far away, called S, then in this Cartesian coordinate system, we have different distances for these two microphones. And because of this extra distance that the wave is propagated for this microphone, then M1, there would be a different time of arrival introduced for this microphone. And that depends on the distance, this angle, and also the speed of sound. So the sound propagates from this place to this place, which is the microphone, with the speed of c, which is almost 343 meters per second. And it depends on these factors, theta and so on. Using this, we can actually do the localization. One very good example of this is the Wall Street Journal data, which is captured in a room using the 8 microphone array. So there's a microphone array with 8 sensors, 8 microphones, in a circular geometry. So that's a planar, 2-dimensional surface, circular surface, which microphones are actually placed equidistant with each other. And people are around talking. For example, there are 4 seats here. There might be some noises from different people talking around in different places, and noises from fan, computer, air conditioner, and many, many other things. So if you, for example, want to locate or get the signal from this guy here, the signal both goes in the direct form, the direct propagation, as well as the reflected versions. So because it's a physical wave, so it directly goes to the microphone, but also it goes to the walls, surfaces, and the roofs, and it's reflected back again to the microphones. But the path which is spent for the direct one is not the same as the one which goes for the reflected versions. Okay? So that's why we have here the reflections, which are called reverberation. Reverberations are reflections of the same source coming back at later time to the sensors. And the same thing happens for the other speakers. So the first goal is how to localize the sound. There are 3 different versions or the techniques to localize a source. Here, acoustic source. It can be used also for the radar. So what I say here exactly goes for the radar. But for the radar is a bit simpler. I'll tell you why. The first difference is that radar tracking system is active tracking. What does it mean by active? It means that we have a transmitter, transmits a signal with different frequencies, transmits over the entire space, 3-dimensional space, and then when it hits an object, is reflected back to the receiver, and based on the time it takes to go and to be back, it says that there is an object in this distance. Okay, that's called active tracking, because you send a signal and you get a signal back. You know what you have already sent, and when you get back something which is similar to what you have sent, then it means there is a kind of object in front. And even they can figure out what is the type of that object based on the reflections, attenuations, and so on, if they have prior information about environment and the materials, they can understand it. But there should be different resolutions based on how many pulses they can send and be back and so on. The other difference is that what we send in the radar tracking system is normally some specific frequencies. So it's called a narrowband signal. Narrowband means very low frequency. I mean very like a tone. It's not a combination of the frequencies. But for the speech case, it's harder. Why? Because speech is a spectrum which is almost wide. So speech is a kind of, it's not a narrow band, it's a wide band signal in general. And it's harder to catch the speech localization. So don't forget, whatever I say here is also usable for the radar tracking and for the radar systems. The first idea is, well, it's better. It was much better to start with the third one and then the second and the first one. I just made a mistake for the order of these three statements, but doesn't matter. One of the ideas is just generally statement is the SRP method, which is called the maximizing the steered response power. Steering, locating, steering, response power. So which part of this three-dimensional space gives you more energy or the power? The more power, it means that there is a kind of stimulation of the power, a stimulation of the molecules of the environment. So when you have a more power in the three-dimensional space, if you can get the spectrum which gives you the power is located in this part, it means that there should be a source in that part. So a steered response power is an algorithm normally uses beamformers, so gives different weights to the beamformer to localize every point of this three-dimensional space, and then finally in the pattern it sees that, oh, there is a kind of localization or accumulation of the power in this part, so it means that there is a source in that part. So just based on the idea, you will understand that this algorithm is computationally very costly, because you're going to every single location of the three-dimensional space based on the resolution that you want. So you might have a very wide beam, you might have a very localized beam. But if you have a very localized beam, then you can have a very good location finding with a good resolution. But the point is that there are a number of the grids that you have to search for then to come to the point. So it's very computationally costly. And if you make it a wide beam, you can much faster go to the end. But the point is that then you find this part of the pattern is together with a high energy. But because the beam is already wide, so the resolution is not good. So that's the problem of the steered response power. It's a very good method, specifically when it comes with the phase transform compensation. It's called SRP FAT. It's the best, almost the best localization method found today, but it's costly. And most of the time it's not possible to apply this in real time tracking. Another method is based on the spectral estimation. It's mostly used for the radar than for the speech case, because the spectral estimation, or finding the peaks in the spectrum of the signal, is mostly available for the narrowband signals. But for wideband signals, it's together with many errors. So people are not normally using this method for acoustic source localization, but they use it frequently for radar tracking. And the third one, which is more prevalent than any of the two methods, is called, generally it's called TDOA estimation or GCC method, or generalized cross correlation, which is actually what happens in natural way for your ears. So that's why we talk about this one, and then we just briefly talk about the first method also. So for the TDOA estimation, TDOA is time difference of arrival. That's exactly what I explained. You have different distances for the microphones. Different distances, it includes, introduces different time arrival, because the speed takes a while to propagate for longer distance. That's the point. So time difference of arrival locators, it normally contains two steps. One of them is TDE, or estimation of the time difference, and then based on the array geometry, you can solve a simple optimization problem, and based on optimization problem, you can find the location of the signal. Okay, so I'll stop in this slide.